Okay, so welcome to the next video. This is going to be a short video because we're nearing the end of the lecture. So it's going to be mostly an introduction, and we're going to resume whatever we don't finish. We're going to resume on next Tuesday's lecture. So I foreshadowed this topic in a previous question. The question that foreshadowed this, if you remember, is we had two positive charges at opposite ends of a square, and we had a negative charge at one of the empty spaces, and we wanted to know its speed when it reached the center. And I set this problem up for you, and I illustrated for you we were not able to do it using dynamics because the electric force, or the Coulombic electric force in this case, the Coulombic electric force was not constant. And because it wasn't constant, this led to, a non-constant acceleration. And if you have a non-constant acceleration, you were not able to use kinematics. So that's what motivates this discussion here. Now, we've been through the same story before in 136. We motivated this with, say, gravity, gmm over r squared, and then we looked at the gravitational potential energy of gmm over r. However, there is a sort of simplification. If we are near the Earth's surface, then gravity is mg, so the gravitational energy is mgh, granted. The other variable force we learned in Physics 136 is springs, Hooke's law, F equals kx. That's a variable force. The longer the elongation, the stronger the force. And we had to use this upcoming information to solve for the energy of 1/2 kx squared. So it's the same story, it's just we're now applying it to a different force. So just to recall, because it's been a while for many of you, even if you were in 136 with me, it would still have been a while. If you weren't in 136 with me, it would have been even longer. So how do we use energy to solve this sort of non-constant acceleration problem? We integrate, pretty much is what we do. So we have this notion of work done, and in high school we tell you the work done is FD, and we might even throw a cos theta somewhere in there. Now, if you were to plot that, if you have a function f that's constant with time, then if you were to graph that, it's just a horizontal line. So how do you interpret the value of FD, or how do you interpret the value of work done? Well, if you have the force is altitude in the y value, and d is the distance in the x value. So you're going to have x times force. That's simply the area of the rectangle. More specifically, this is saying that the work done is simply the area under the force versus displacement curve. And in the event the force is constant, calculating that area, a 2-year-old can do. Maybe not 2-year-old, maybe like a 4 or 5-year-old, but multiplication, simple multiplication, F times D. However, what if we had a variable force, a force that changes with time? Well, what you do is you can approximate the area under the graph using many small rectangles. You've seen this done in first-year calculus, whether you take 134 or 135, or I don't know if there's the same course code downtown or at St. George at Scarborough, but first-year calculus, it's all pretty much the same. What you can do is you can say, okay, well, the work done is approximated by the work done in rectangle 1 plus the work done in rectangle 2 plus the work done in rectangle 3 plus the work done in rectangle 4, et cetera, et cetera, et cetera. And each individual rectangle, you're going to say, okay, I'm going to pretend that the force over a small rectangle, I'm going to pretend that it's constant. And then I'm going to multiply by the width of my rectangle. And then in my second rectangle, my force will be slightly different. So F2 delta x, and then F3 delta x, and then F4 delta x. And it goes on and on and on and on and on until you're done. That's a good approximation. It's also really tedious. Now, if you remember your calculus, not even not even robustly, just the notion, you'll know that this is the precursor to an integral. It's called a Riemann sum. So here you have the work done is the sum of all the individual rectangles. But if you shrink the width of the rectangles to be very, 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 very small, then the Riemann sum becomes the integral. And this is actually the real definition of work done due to a particular force. So what does that tell us? If we have a non-constant force, we can't simply just multiply by d. We have to integrate. So here, without really dwelling on the details, we have a Coulombic force, I might add. If we have a Coulombic force, we have k q1 q2 over r squared. If we integrate that, we're integrating that to get the energy, and we're going to get minus k q1 q2 over r squared. So that's the indefinite integral, obviously. If you take the definite integral, you can play with the negative sign as you see. Oh, sorry, there should not be a square there. I was getting carried away. So kqq over r. Now, when you do the indefinite integral, you do get the negative sign there. If you take the definite integral, you can play with the integration bounds if you'd like, and you can may or may not be able to get rid of the negative sign. It doesn't really matter. I'm not a huge fan of nitpicky mathematics, if you haven't noticed. You can easily account for that negative sign by thinking of your conservation of energy equation. Is your situation adding energy into the system, or is your situation removing energy out of the system? And with that simple sort of thought process, you can figure out should it be a negative or a positive. So this is for the Coulombic force. So I would say the Coulombic electric energy is E equals k q1 q2 over r. That's the Coulombic energy. And we had to do this because it was a variable force, so we had to integrate to obtain the energy. However, the second situation we just recently saw was the parallel plate capacitor had a constant E field. And a constant E field means a constant force. And if we have a constant force, I mean, I suppose you could integrate if you wanted to, but you know, when you integrate a constant, you're just multiplying by x, right? So in this case, work equals FD, because the force of a parallel plate capacitor is a constant value. So here we see that the work done in a parallel plate capacitor is QE, because that's what force is, times the distance you want to move, the distance you wish to move this hypothetical charge. And you can drop the brackets to say QED. Now, for those of you who remember grade 11 math, when you had to do trig proof, left side equals right side, you always put QED at the end of your trig proof, quanderat demonstratum. It's a little funny math joke. We have a physics formula that spells QED, ha 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 ha. Very bad physics joke, anyway. But no, Q would be the charge of the particle that you wish to move. So let's say we had like an electron in this parallel plate capacitor, and we want to move this electron, you know, to the right. Well, Q would be the charge of the electron, the E field would be the electric field of the plates, and then the D would be the distance at which we wish to move the electron, whether it be 1 centimeter, 2 centimeters, 9 centimeters, or what have you. So showing you these two things, I wanted to sort of illustrate a caution. Very few scenarios in real life, I might add, in real life, have a constant E field. So most of the time, if you were an actual scientist or an actual physicist, not an actual scientist, all of us are scientists, physicist is what I meant to say. Very few scenarios in real life have a constant E field. So if you were like an actual practicing physicist, you would most of the time find yourself having to integrate because unfortunately, that's the reality. Work done equals QED. It only applies if the E field is constant. Now, luckily for you guys, we're in a first-year introductory physics class, which means many of the problems you might see in a textbook might artificially have a constant E field, right? Because we're in a hypothetical textbook setting. Please understand, in real life, the real world does not behave so elegantly. But luckily for you, just to get your feet wet and familiar with the material, there will be many, not all, but many problems will have constant E fields. If you do find yourself needing to know the electric energy for a non-constant electric force, you would just fall back on the integral. Okay, so here's an example of what we just talked about. I don't want to launch the poll because we're running out of time, so I'll just talk about it. A proton and an electron are in a constant electric field created by a positively charged plate, blah, 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 blah. Okay, you release the proton from the positive side and you release the electron from the negative side. Which one feels a larger electric force? Well, we look at the electric force in the parallel plate capacitor. So the electric force is going to be QE, and this is going to be E of the parallel, or E of the capacitor. And this is going to be either the Q of the electron or the Q of the proton, depending on which scenario we're looking at. So the electric field in a parallel plate capacitor, we know, is going to be the charge on the parallel plate capacitor, the area of the plate capacitor, and epsilon naught. So which one's going to feel a larger force, electron or proton? Well, the E field is the same in both cases, and the charge on a proton is equal but opposite of an electron. So the answer is going to be the same. Where is there? C. They both feel the same force. Okay, yeah, sorry. They feel the same force, but opposite direction. I should be more diligent and read all the options. So yes, same magnitude of force, but opposite directions. Okay. Here they talk about kinetic energy. This one's more relevant because we've introduced the notion of energy now. So which one is going to obtain more kinetic energy? Well, we know the work done on a charged particle is QED. So if we release a proton from here, it will feel a repulsion from these positive charges, and it will move toward this plate. By the time it reaches this plate, it will have moved a distance d. So the work done is going to go into 1/2 mv squared, or more specifically, it's going to go into EK. Well, we notice whether it's the electron or the proton in either scenario, it's the same magnitude of charge, it's the same electric field, and the electron will be released on this end and travel backwards. Same distance d, but just in the opposite direction. So in both cases, QED equals the kinetic energy in both cases. And so the answer is going to be they both acquire the same kinetic energy because they happen to have the same charge. Now, it's not E because there is no such thing as a negative kinetic energy. You can't have a negative kinetic energy. If you're wondering why this is, even though the charge on the electron is negative, the displacement is negative. So the two negatives cancel out, and then you mathematically get a positive again anyway. So the answer is going to be C, and it's because of this equality right there. QED is going to equal to the kinetic energy. Okay, moving right along. I know we're running right short of time, but moving right along. Which group of charges took more work to bring together? Well, in scenario A, what is the total energy of the system? Well, the energy of the system is going to be the energy between the two particles. The two particles are going to be K, Q, Q, or Q1, Q2 over R. And in this case, it's going to be K times 2 times 1 over D. So this is going to be 2K over D. The energy in this system is a little bit tougher to find. The energy in this system is going to be the sum of the energy of each pair of charges. So we have this pair of charges, we have this pair of charges, and we have this pair of charges. We've got 3 pairs of charges here. So we're going to have K, Q, Q over D plus K, Q, Q over D plus K, Q, Q over D. So that's going to be 3K times 1 over D, or 3K over D. So which one has more energy? 3K over D is larger than 2K over D. So the answer is going to be B. There, 3K over D is larger than 2K over D. So the answer is B. Okay. This worked problem is very similar to literally what I just did. The trick here is well, you know what? I don't want to rush it. We'll do this one on Tuesday. And this is actually the end of the scheduled material for today's lecture anyway. So we were only 1 problem short of our schedule, which means I think we're pretty much right on track. We will pick this up on Tuesday because I don't want to rush the solution for you, because it's important that it gets explained properly. You could also look at a very similar example problem in your textbook. So I would strongly recommend maybe reviewing your textbook, and you can get a sort of a head start on understanding this problem before Tuesday's lecture. Okay, so thank you for joining. The energy portion is quite short because we were piggybacking a lot for 136. The only thing different is I was sort of reintroducing the notion of having to integrate a variable force and showing you that for Coulomb's law you need to, but for other scenarios such as the parallel plate capacitor, you don't need to. So energy is pretty much done. It's just a matter of going back and practicing in your textbook, reviewing concepts such as the conservation of energy, doing some practice problems in tutorial in your textbook on the assignment that practices the flow of sort of kinetic energy into electrical energy and vice versa. So you can become more comfortable with that. And then on Tuesday's lecture, we will do this question, but we will very promptly move on to a new idea such as capacitance and voltage and what have you. So thanks for joining us on our second video. I will stop the recording now and see everyone on Tuesday.